You have fallen into Event Horizon with John Michael Godier. John is joined today by Dr. Sean Raymond. Dr. Sean Raymond is a director of research at France's Centre National de la Recherche Scientifique, based at the Bordeaux Astrophysical Laboratory. He received his PhD in astronomy from the University of Washington in 2005.
Sean Raymond, welcome to the program.
Thanks. It's a pleasure to be here.
Sean, one of the great questions of my life is how Earth got its water, because there are a lot of mysteries hidden in there, as you know, and tell me about those.
Yeah, that's a big question. And it's one that I've been kind of studying for a good chunk of my career. So when I started in this game of like trying to jump into my PhD thesis was about how planets form, about how planets like Earth form. Obviously, we care most about Earth of all the rocky planets out there. And so, the general prevailing thought about how Earth formed is it forms kind of growing from the collisions of these big rocky things bashing into each other. And a key part of that is where this little bit of water we got came from. And it's not really that well appreciated how little water Earth has. Earth has, like all told, about 1 part in 1,000 water. And it's not actually that well known. We know how much water is on the surface, and we have some kind of guess about how much is in the mantle trapped in rocks. But how much is in the core is a big debate. There could be quite a bit or could be almost none, depending on which geophysicist you talk to. And the story of how the water got there is it's a whole kind of rambling story that's changed what it looks like over the years. And so do you want me to just go through it?
Absolutely, but I got a question to interject. So, plate tectonics, which might be very important for life, again, as you know, seems to involve water. So incorporate that into your explanation to me.
Oh yeah, that is an important part of the story. It's generally thought that plate tectonics is helped out by water because water trapped in certain minerals within the mantle decreases the viscosity of those minerals, which makes it more likely for plate tectonics to be able to happen. Basically for rocks to be able to kind of slide past other rocks. And so that's kind of an important part of the story. In terms of where the water came from in the first place, when I was starting off in this game, there'd already been one kind of shift in thinking. So let me jump back past that shift to the state of the art in the 90s. And back in the 90s, the story was this. Earth, all the building blocks of the Earth, the rocky stuff that went into creating our planet, they were basically dry. And so the prevailing theory then was that Earth formed dry, and then a later bombardment of kind of comet-like stuff, comets basically. That is where the water came from. It came from these comets. And shortly, that idea had been around since, I'm not sure when it was first presented. It's around since at least the 80s. Then starting in the 80s and 90s, people started measuring the isotopic signature of water. So both the isotopic signature of water on Earth, which is basically the only isotope that's useful, is called deuterium. And so it's basically a proton with a neutron versus just a proton. So deuterium versus hydrogen, normal hydrogen ratio. So this isotopic ratio, it's kind of like a fingerprint is what you can think of it like. It's like a fingerprint of this kind of special kind of water we have on Earth. And people started measuring that, and they noticed that the water that we have on Earth is a pretty good match to some kinds of meteorites that we have, but it's not a very good match to comets. So basically, there were kind of two big factors that killed the comet idea. One of them was this idea that the isotopic fingerprint of cometary water is just not the same one we have on Earth. And there's new wrinkles in the story, but the key one in the 90s, they showed that the isotopic fingerprint of this cometary water was not the same as Earth water. And so that makes you think that maybe comets didn't really do the delivering of water. And kind of I think what I think is much stronger evidence is that people did orbital models, basically dynamical models of how comets actually come to crash into the Earth. And to do that, they have to come from the far outer reaches of the solar system They get scattered, gravitationally slingshotted by the giant planets, each one in turn. And then Jupiter kind of launches them on trajectories that cross Earth's orbit. And when things go just right, a comet can then bash into the Earth. But it turns out that the odds of that happening is really, really small. It's like 1 in a million kind of odds. And so we know some comets did crash into the Earth, but their numbers were actually very small and way too small to explain the water on Earth. So that kind of killed the whole comets bringing the water story. So now jump ahead to the early 2000s. There, the idea was that the Earth's water instead came from the same place that these meteorites got their water. So these meteorites that have the same isotopic fingerprint as Earth's water, those meteorites come from the outer part of the asteroid belt. They're called C-types, if you care, or carbonaceous meteorites.
Carbonaceous chondrites.
Exactly. Carbonaceous chondrite. Exactly. And so those types of meteorites, they came from the outer asteroid belt. Somehow they got scattered inward. And so the idea there was that the meteorites were incorporated into the Earth as it grew. Over the years, we kind of changed that idea a little bit. So instead of things coming from the asteroid belt and then bashing into the Earth, now we think that you have to rewind the story kind of one kind of prequel earlier. And instead of those asteroids being kind of the parents of the objects that bash in the Earth, we think they're more like the cousins. And so we think one big population of this kind of carbonaceous chondrite, like water-rich asteroid stuff, those objects all started off out past Jupiter. As Jupiter and Saturn grew, they tossed them all over the place. Some of these things went and got trapped in the asteroid belt. Some of them went past the asteroid belt and bashed into the growing planets. And then some of them got kind of launched into interstellar space and never came back. Right? But the ones we see are the ones that stuck around. And so the ones that we see in the asteroid belt now are like the cousins of the ones that crashed down on Earth. And we don't see them anymore. We just see the water that they deliver. So that was the predominant model for a while. And now things changed again a few years ago. And the key part of the story that changed a few years ago, which is still hotly debated, and so there's still kind of some uncertainty in it. And this part of the story comes from people who measure meteorites ridiculously precisely. What they found is that those building blocks, the rocky building blocks of the Earth that I was saying are completely dry. Turns out they're not completely dry. And they actually have, if you look carefully enough, they have some hydrogen trapped in them. And so if you actually built a planet out of this stuff, that hydrogen would combine with some of the oxygen that's trapped in some of the rocks and make water. And it would make water in enough abundance to explain most of Earth's water. And so if that's really true, and there's some debate about whether that's contamination or not, but a lot of people think it's real. And so if that's real, then the measurements have gotten precise enough that we think that about 2/3 of Earth's water was native and came from this rocky stuff that the Earth was built from. But there was still this contribution from carbonaceous chondrite, this inward scattered water-rich asteroid stuff. And so even though that inward-rich water, inward scattered asteroids, they have a lot more water. So only a small fraction of Earth's mass probably came from those objects, but they probably delivered maybe 1/3 of Earth's water. So that's kind of where we're at right now, where Earth's water is a mix. Some of it was local and some of it was imported. So that's the current thinking, but it's still kind of, there's details being worked out here and there.
Okay, so what role does the sun play in this? In other words, all right, so did these objects, these carbonaceous chondrites, giant carbonaceous asteroids, once have much more water than we could see now with them? And has the sun sublimated and blown off most of the water that they originally had during the early solar system? And they can't deliver water like this now if they were able to.
So that's a good question. If you look at meteorites now, even among these carbonaceous ones that have a lot of tar, they basically have a lot of carbon stuff. That's what they're called, carbonaceous. They have a lot of carbon and other volatile stuff stuck in there. They range from being pretty dry to containing a lot of water, like 20% water by mass. That's 200 times more water concentration than we have on Earth. And so there's a big range. And meteorite scientists kind of can play these games and figure out based on the mineralogy of a rock, kind of how much water had to be there at the start. So even though some water may have gotten lost, some was trapped in minerals, and they can kind of figure out there must have been at least this much water at the start to end up with what we see. And so just like you're saying, these rocks probably started off with more water. Exactly how much more is hard to tell, maybe up to 20% by mass, like we see in some of these things. And so they probably had a lot of water. They lost a lot to space. They lost a lot during collisions. Even when they bashed in the Earth, not all of the water was necessarily incorporated into Earth. But, a lot was lost to space for sure.
What do you think that Earth looked like when it was getting this water? Do you think it had more? Do you think it was more of a water world than it is today? Or what do you think the profile of this planet looked like, especially during abiogenesis?
That's a good question. The typical picture, up until recently, the picture of the early Earth has been that it was getting bashed so much that you think of it as kind of like a magma ocean. There's a term for this, a magma ocean, basically where the surface of the Earth is basically molten rock. But in recent times, that's actually changed because people have been doing really complex modeling of how planets cool off when they have early primordial atmospheres on top of them. And so the Earth's atmosphere at this time was not like it is now. It probably was mainly hydrogen because it had grabbed onto a little bit of hydrogen, which is the predominant gas in the disk from which the planets formed. Basically, Earth's surface probably went through phases where it was completely molten by giant impacts, was heated up enough, and then it cooled off after a certain amount of time. The amount of time it takes to cool off is one of these things that's been calculated more and more precisely lately. And it probably cools off in maybe 100,000 years or a million years. And so during Earth's growth, it had different phases of having giant impacts. So a few of these giant impacts created these magma oceans that hung around for a while. Then it cooled off. And then after that, it was kind of like was there water on the surface at that point? Or was it just kind of bare rock? That's a good question because there's some amount of time that's required for water to end up on the surface. So that's a really good question. And I'm not sure of the answer of that. I'd have to ask someone who models this more carefully, and they would tell me. I can imagine what they would tell me. Well, it depends on these factors that we don't know too well.
Yeah. And that's the scary thing, but that's going to lead us into a discussion about exoplanets and what effect the solar system had on this. Why is the solar system different? But we'll get to that question. Moons. Can a moon orbit a moon of a planet like Earth? I mean, in other words, could our moon have had at some point, or form, whatever happened, capture another moon and it orbit around it instead of the Earth?
Yeah, this was a really fun project that I did. You probably saw a blog post I wrote about it with my friend Juna Kohlmeyer, where her son came one day and was asking her whether a moon could have a moon. And she's a fancy astronomer and she's super smart. She's like, I don't know. And she came to me and asked me, and I was like, I don't know. And so we thought about it more and we asked some other people. And in the end, we ended up kind of using the analogy of a planet really close to a star. People had done calculations of whether planets that are very close to their star, basically hot Jupiters, could hold on to their moons. And so we had the idea, well, that's kind of a metaphor for replace the star with a giant planet, replace the planet with a moon, and then the other moon would be like the moon or the submoon. And we did some calculations of that. And so it turns out that in theory, in very simple math land, it's possible for submoons, so moons around moons, to exist. They are more likely to be stable for long time periods. The main thing that can destabilize them is tides, tidal effects due to combinations of the planet and the moon. They're more likely to be stable. Moons are more likely to be stable if they're a little further away from the moon itself and more massive. Now, in reality, can this really happen? Because in reality, real moons are not the point masses that we assume. So, for example, orbits around our moon are almost never stable because of what's called mass cons, which are mass concentrations, just an abbreviation of mass concentration, which is just basically the mass in the moon is not perfectly evenly distributed. And so its gravity field is not perfectly smooth, and that disrupts moons' orbits. So in reality, can moons of moons really exist? I think they can in some kind of ideal situations. we in this paper we found like a few different cases where it was possible. Like around Saturn's moon Iapetus, it's possible to have a moon around that moon. And a cool thing is Iapetus has this weird shape. It has this weird ridge going around it, which is thought to have been from an object that kind of spiraled down and crashed down and got torn to pieces and left behind this ridge. So it's as though it used to have its own submoon that got destabilized for some reason and crashed down. It's kind of cool.
So, big question. The big question. All right, Earth has water. The moon is very dry. How did that happen?
Oh, good question. The general thinking about that is that the moon and the Earth formed from basically very similar stuff, and the moon just had trouble holding on to the water. So they probably formed with similar amounts of water somewhere in there. The moon, we think that the moon itself, like its origin was that it was the last giant impact into the Earth of another really big object that we call a planetary embryo, kind of a protoplanet, bashed in the Earth, may have created a disk of kind of rock vapor around the Earth, or it might have done something slightly different and just kind of launched off a chunk. But either way, the moon was a result of this giant collision. So given how much heating happened and the fact that Earth has a lot more gravity than the moon, Earth could hold on to its water a lot better than the moon. And so basically the moon probably has a little bit of water in its interior, but much less than Earth just because it couldn't hold on to it. That's the simple answer.
If the Theia hypothesis is correct, which we don't know, but say Earth, was a glancing blow that threw off the material for the moon, could Theia have delivered water to the Earth?
Ooh, this is an interesting idea. This idea was thrown out there a few years ago that Earth was completely dry except for one gigantic water-rich impactor that happened to be Theia that was also the moon-forming impactor. And so it turns out that's pretty unlikely, but it's not impossible actually. The current thinking as of like right now is that Earth might have only gotten bashed by a few of these relatively big carbonaceous chondrite-like objects, but maybe big ones. And so instead of having a whole rain of small asteroids, there were just a few big ones. And one of the big ones could have been part of Theia, the moon-forming impactor. So it is actually plausible that it sort of went in that direction and that Theia did deliver some of Earth's water.
Now, that is very complicated. Piecing together the inner solar system during the very early solar system is complicated. How do you do that? I mean, that's hard. As a scientist, how do you try to weed through something that is extremely complicated like this?
So the hard part about understanding like planet formation in general and solar system formation especially is that it's not one field of study. So it's not like you're studying stars and you can just go to conferences about stars and read all the books about stars and you learn everything there is to know about stars, even though stars are complicated on their own right. Planet formation itself sits kind of right on the intersection of several different fields of study. And so one of them being study of meteorites and the chemistry aspect of that especially. Another one being kind of how orbits work, orbital dynamics we call it. And things flying around, how often do they bash into each other? How do the orbits of growing planets evolve in time? Another another key field there is the study of planet forming disks. This is kind of the birthplace where the action is actually happening. It's easy to kind of overlook the disks or think they're not that important, but the detailed structure and evolution of the gas disks from which planets grow is really fundamental to the whole process. And it turns out in some of these models, if you change a couple parameters, the outcome changes enormously. It's really interesting. And so that's kind of the input parts to solar system formation. And the outputs are what we see right now. And so that's kind of things like where the planets are, studies of asteroids and comets and meteorites. And also, if you want to understand the bigger picture that maybe we'll talk about later, you want to put the solar system in a bigger context. And then the field of exoplanets also comes into play. The reason this is a hard thing to do is ideally you would want to be able to kind of zoom out enough to have a vision of the big picture and see that there's a lot of different pieces that have to fit together. And if you come up with a great new theory about one part of the story, it really has to fit with other parts of the story. Otherwise, it makes no sense. And this is a very common thing in science, of coming up with one awesome, amazing idea that just doesn't seem to fit anything else in reality, which is always a shame, but it happens surprisingly often. And so that's kind of I think the biggest challenge is really understanding all these different things. And so I spent years going to conferences where there'd be talks by meteorite people and just being like, what the heck does this mean? And I just had to have it bashed into my head enough to have some idea about it, and understand. I came from the astronomy side, and so I had an easier time understanding the parts related to orbital dynamics and exoplanets and the disks, but a big struggle understanding what the point of the meteorite analysis was. And now in time, I'm recognizing more and more how vital it is to really understand that part. So this is the challenge, really. You don't have to be an expert in one thing. You have to ideally be an expert in like 5 different things.
Yes, and I'm going to ask you to be an expert in 5 different things with this one. Protoplanetary disks, when we look in infrared, and this started, before IRAS in the 80s, and we were looking at protoplanetary disks. What clues do we get about the formation of the solar system from what so far we have seen, and James Webb's probably going to help this, from these disks around younger stars than the sun?
Good question. So yeah, studies of observations of disks around stars are telling us all sorts of stuff. And the most important tool we have for that, I think ever, but the current best tool we have for that is called ALMA. It's a radio telescope, this giant radio telescope in Chile on the Atacama Desert. It's the Atacama Large Millimeter Array. It's this gigantic array of radio telescopes. And ALMA is sensitive basically to wavelengths of light that are around a millimeter. And what's interesting about that is that's the size scale of dust that ALMA is most sensitive to. And it turns out that during the growth of dust grains into bigger dust grains within gaseous protoplanetary disks, there's a certain size scale at which the dust starts to move relative to the gas. And so dust kind of gets drifts around. The idea is that very, very small dust grains just get blown in the wind. Literally, they just kind of go wherever the wind is, which is wherever the gas is. And really big objects like planets, they don't really care about the gas because they got so much inertia. They're so big. They got so much mass. But there's an in-between size scale where objects get pushed enough by the gas, but they don't have enough inertia that they end up losing a lot of their orbital energy. And so what does that mean? It means they end up spiraling in or sometimes out, but usually inward. And so they actually can move around through the gas. And what's cool, why I bring this up, is because ALMA is particularly sensitive to objects that are just about that size, it turns out. And what's really cool is that with ALMA has taken images of I don't know how many, several dozen planet-forming disks now. And what it sees is that these disks almost generically have weird structures. They're not just kind of smooth disks. When you look at where the dust is usually in rings, or sometimes in other weird structures, but often in rings. And so what does this mean? We think what it means is that dust is indeed drifting around within these disks. So the gas is still smooth, but the dust is clumped in certain special locations. And there's a big debates that vary from system to system about whether planets have already formed and it's planets that are shaping exactly where this dust is, or whether we're looking earlier in the process and planets are going to grow out of this dust. And maybe it's a combination of the two.
Huh, that's interesting. So it's shepherding, like Saturn's rings. Or maybe it's not, right?
Yeah, exactly. So there's one very specific case called PDS 70, where we have images of 2 planets within a disk. And then we can also see where the dust is. So in that case, we know the planets are already there. But for the vast majority of cases, we can't see the planets themselves if they're there. And so then we have to kind of come up with some kind of indirect models and test them against what we see.
Any idea on how you would end up with a differentiated ring around a star without a planet? How's that happen? I mean, what's the physics of that?
So this probably has to happen early in the game anyway. And so the idea for how we think that kind of the first big solid objects form, that we usually call planetesimals. So the standard theory for how planets grow was first developed by this Russian dude named Safronov, starting back in the 60s. And his general approach was to assume that there was this big swarm of objects that he called planetesimals that bash into each other and make the planets. And he's not the first one to come up with this idea, but he's the one who kind of put the current math that we use into it. So how do planetesimals form? Over the past 10 or 20 years, there's been kind of a lot of work to explain how that happens. And now we have a pretty good idea. And so we think how it happens is that these dust grains start off, they're just getting blown around the wind. They bash into each other. They grow to this kind of millimeter scale where they can drift around. They're often called pebbles at this, for some reason, at that scale, but whatever. They're big dust grains. They start drifting around. And if nothing happened, then you might imagine they would just kind of drift and just go until they reach the star or the inner edge of the disk anyway, and they would be gone. When you look in more detail at what's going on within the gas part of the disks, it turns out that gas disks are probably not perfectly smooth. There are little regions that have little bumps in the local pressure, and that acts to basically slow down the drift of dust. And so when dust is drifting inward, they can get one of these little bumps and they slow down and get concentrated, excuse me. And so they slow down and get concentrated, then more and more dust grains end up in this one location. And then when you have a sufficient concentration of dust, it can actually clump directly and form much bigger objects, things like planetesimals. And it's really cool. Basically, once you have this concentration of dust, it actually helps concentrate it more by this instability called the streaming instability. And then you form these big objects. And so what's the key thing here is basically that you just have to have enough of a concentration. And like I said, it's generally thought that that comes from little blips, little substructure within the disk, that basically the gas itself is not perfectly smooth in all of its characteristics either.
Sounds like the Big Bang and the cosmic microwave background radiation, where you have anisotropy. And why is it a clumping? Why is it clumping? Now, our solar system, to sort of switch gears, is weird, as far as we can tell from the exoplanet systems we have seen so far. And why is that? Why do you think that is? And I know that's a huge question, but hypotheses?
Sure. So, well, here, let me do a little quantification, a little kind of anecdote I like to do about, or a thought experiment I like to do about how weird the solar system is. So the solar system, if you viewed it from a distance, one question you can ask is, well, which of the solar system planets could you see if we were observing, the solar system with our own present day technology? And it turns out the only planet you could see is Jupiter. If there was a survey, a radial velocity survey for at least, 10, 20 years of this distant star that's the sun, then you could pick out the radial velocity signature of Jupiter. But you couldn't see Earth, you couldn't see any of the rocky planets. You couldn't see Saturn or the ice giants. So all you could see is Jupiter. And so when you compare Jupiter with the demographics we know of exoplanets around sun-like stars now, about 1 in 10 or so of sun-like stars has a Jupiter at all. And then the orbits of most Jupiter mass or Jupiter sized planets we know are much different than our own Jupiters. They tend to be much closer in, or more often actually much more eccentric. Their orbits are much more stretched out. They're not almost circular like our Jupiters. And so basically, if you put those two factors together, there's about a 1 in 10 chance of having a Jupiter like ours, and about a 1 in 10 chance of that Jupiter having an orbit similar to our own Jupiters. And so put together, that means our solar system is kind of a 1% oddball among sun-like stars. And that's just from what we can see, the only one planet we can see. And so it could be that the solar system is much, much less common than that even. That doesn't mean that every given population of planets has to be much less common. Maybe planets like Earth, at the same distance as Earth, same size as Earth, are very common around sun-like stars, but we can't find those yet anyway, so we can't tell. But as a system, the solar system is definitely weird. And so to your real question, why is that? I think the answer, at least the answer that we've kind of been converging on, is that the solar system is kind of in this in-between place. And a lot of it has to do with Jupiter, probably. And so Jupiter seems to have formed pretty fast, and it seems not to have disturbed the rocky planet's growth too much, because we're still here. And we think that it formed fast enough to perhaps prevent some of that drifting dust that I was talking about to get to where the rocky planets were already growing. And so that may have prevented them from growing further into, faster into bigger things, and to become super Earths or something like that. And so part of why Earth is small may have to do with Jupiter. That's one possibility anyway. Another kind of part of the story is, like I was mentioning, Jupiter's orbit is much more circular than the orbits of most Jupiters or most gas giants we find around other stars. Now, we still think that basically, why do these other gas giants have such stretched out orbits? The current thinking is that what we're seeing is basically the survivors of some big instability, a dynamical instability. So what's a dynamical instability? We think that planets, basically, anytime a gas giant forms around a star and a disk of gas, probably another gas giant forms. There's probably enough stuff to form more than one. So probably two or three or four or five form. And when that happens and the gas starts to go away, what happens? Well, each of these planets has so much mass that unless their orbital configuration is just right, they often go unstable. And what this looks like is that over the period of, 100,000 years, these planets kind of jostle each other. They gravitationally perturb each other's orbits, kind of stretching them out a little bit here and there until the system breaks. And when it breaks, that means the orbit of one planet crosses the orbit of another planet. And since these planets are so massive, they have such strong gravity. And these are for planets that are not right close to their stars like hot Jupiters, but out like where Jupiter is now. They have such strong gravity that it's very unlikely that two planets will actually collide. It's much more likely for these kind of planets once they come close to each other, to give each other these giant gravitational slingshots. And they keep doing this until one of them gets enough of a kick that it flies off away from the star and it never comes back. It's ejected into interstellar space. And then that keeps going among all the survivors until whatever planets survive are far enough apart that they're not going to, get into it anymore. They're done. And after that process happens, the surviving planets universally have much more stretched out orbits, much more eccentric orbits, we call them. And the distribution of the shapes of the orbits of gas giant planets around other stars is consistent with basically all of them, almost all of them, say 90%. 90% of all of the systems of gas giants that we see are the survivors of these kinds of instabilities that launch some planets off into interstellar space, and the survivors are these crazy stretched out orbits. Now, let's look at our solar system. Our solar system is in this weird in-between spot where we have two gas giants, only two, not three or four. And their orbits are a little bit stretched out, but not that much. But it turns out that to reproduce a bunch of different observations of the small body populations in the solar system, things related, basically the asteroids, different populations of moons of the giant planets, the asteroid belt and the Kuiper belt, you can reproduce all of those in one shot if the giant planets did actually have an instability in our own solar system. But what's different is that the instability in our solar system was pretty wimpy. So Jupiter and Saturn never gravitationally slingshotted each other. They probably did with, one of the ice giants. And there was probably even an extra ice giant early on that was itself ejected. Or maybe, kicked off to become Planet 9, maybe.
Super Earth.
Yeah, something of that size. Something like an ice giant size thing, of 5 or 10 or even 15 Earth mass object kicked out. But Jupiter and Saturn never scattered off each other. Because in our simulations, if things go a little bit wrong and Jupiter and Saturn scatter off each other, then Saturn's ejected, Earth gets dumped onto the sun, or Earth's building blocks get dumped on the sun. And in the end, all you see at the end is Jupiter with a much more stretched out orbit and no other planets, which is what we see among lots of exoplanet systems, but not our own. And so one of the factors I think that why Earth is different is because even though I think we had this instability, it was much gentler. And exactly why it was gentler, we don't know exactly why. But it seems like that had to be the case.
Let's get complicated. So Jupiter, some people think anyway, that Jupiter was wandering around the inner solar system at one point, may have formed in a different part of the solar system, and its resonance, its orbital resonance that it eventually achieved with Saturn played in part to this. How did that happen, or do you not subscribe to that?
Well, this is my idea. So it's funny. This is my personal idea, but I don't necessarily subscribe to it anymore. So this is what's called the Grand Tack model. And so yeah, the idea is that basically Jupiter early on formed from gas, right? It's a gaseous planet. So it formed early on while there was still a gas disk around the young sun. And when there's a big planet embedded in the gas disk still has a lot more mass than the planet, and it can basically torque the planet, it's called. The planet launches these cool spiral density waves, which affect the planet's orbit and can cause its orbit to shrink or to grow, usually to shrink. And Jupiter on its own usually shrinks, but Jupiter and Saturn together can, under some circumstances anyway, their orbits can go outward together. And so if that was the case, then the story would be this was kind of the first model that we had that actually matched the rocky planets well. And so basically, in that case, Jupiter would have migrated inward and cleared out the asteroid belt and cleared out a lot of the mass that would otherwise have grown Mars much bigger than it is. Then Saturn formed a little later. Then its orbit shrank down to approach Jupiter's. And when two planets approach each other in this context, they're kind of slowly spiraling together. They're not actually about to collide. When that happens, they can get captured in an orbital resonance. And so we think in this case, it was either the 3-2 or 2-1. What does that mean? That means Jupiter's probably doing 3 orbits for every 2 of Saturn's, or maybe Jupiter was doing 2 orbits for every 1 of Saturn's. But regardless, in either case, there's this kind of special resonant alignment between the two. And in that case, the 2 planets can sometimes spiral outwards. And so if Jupiter went inwards, spiraled inwards, then Jupiter and Saturn together spiraled outwards by this process called migration. It could have cleared out the asteroid belt. It can explain a lot of things about the solar system. And for a long time, this was the only game in town because we were able to kind of shoot down what I call the classical model for how the rocky planets formed. And this was the best alternative. These days, there are a few other alternatives that are just as good and probably more plausible now. But this model called the Grand Tack really kind of pushed the whole field forward quite a bit.
Now, how do you end up with a star system like TRAPPIST-1, where you've got all these rocky planets, as best we can see and characterize, but it doesn't seem to have a gas giant at all?
Yeah, exactly. So this is what we think could have happened to our own solar system if things had been a little bit different. So if the rocky planets, basically if the building blocks of the rocky planets, if there was more mass in the building blocks of the rocky planets, then the planets would have grown bigger faster. And so what does that mean? That means they would have gotten big and massive enough earlier on in the game. What matters here is the lifetime of that gas. So it's like I was saying, all the planets are all kind of forming within this disk of gas around the young sun. There's no gas around the sun now. So at some point, the gas disk went away. And we know from observing other stars, young stars, that gas disks only usually last maybe 5 or 10 million years. So that's really short compared to the almost 5 billion year lifetime of the solar system. And so there's this short window right at the start during which planets can get big and still have this gas disk around. And that's when they can migrate. Their orbits can spiral inward. In the solar system, we don't think the rocky planets did much of that. They probably didn't migrate much at all. Maybe a little bit, but not much, at least not the rocky planets. But what if they had? What would be different? Well, if there was more material to build the rocky planets, then they'd grow faster, they'd get big enough to migrate, to spiral inward. And that would bring the orbits of the most massive planets closer to the star, closer to the sun in this case. But right, so for TRAPPIST-1, it'd be the same kind of process going towards TRAPPIST-1, the star. What happened there is basically all these planets their orbits are slowly spiraling towards the star. And just like I was talking about for the Grand Tack model with Jupiter and Saturn, the planets, as they're kind of migrating together, they don't bash into each other, at least not too often. More often, they get trapped in these special orbital configurations, in these orbital resonances. And so what happens is instead of just 2 planets being in resonance, each pair of planets can be in resonance. And so in the TRAPPIST-1 system, what's really special about it, or one thing that's special about it, is that there's these 7 planets, and each pair of neighbors is in a resonance, a special, an orbital resonance with its neighbors. And so, there's the outer 2 planets are in 3-2 resonance, if I remember right, or maybe 4-3. So the innermost of those 2 is going around 3 times for every 2 of the outermost, and then they line up again. And the same, each pair has this kind of special chain of resonances. So all together, they make this nice resonant chain. And TRAPPIST-1 is beautiful. The fact that we see all 7 of the planets pass between our line of sight and the star itself. So we can see little blips in the brightness of the star itself as they pass, as they transit their stars. That shows that the orbital plane of the planets is really, really thin. And so it's like they still are in the exact same, they're remembering that plane where the gas disk was around their star when it was very young. And so we think that's how TRAPPIST-1 formed, by kind of this inward migration of these rocky planets toward their star in a relatively gentle way until the disk of gas went away, leaving the planets kind of stranded in this special configuration. And what's interesting, I think, is that, at least according to some models that I've helped develop, I think that pretty much all of the super Earth planets that we see probably formed in the same way. About half of all stars are thought now to host these super Earths, right? So planets between maybe the size of the Earth and the size of Neptune or so, with orbits that are much closer in than any of them in the solar system. But most of the time, those planets are not in this nice chain of resonances like we see in the TRAPPIST-1 system. And so why not? Well, we think that what happens is kind of generic, that this process is pretty generic. I mean, that if there's enough stuff, rocky or icy stuff, if it grows fast enough, big enough, fast enough, then planets or planetary embryos, they'll migrate toward the star. So they'll spiral inward. But usually it'll happen a bit faster and kind of more violently in some sense than in the TRAPPIST-1 system. So what does that mean? Basically, if things are moving a little faster, they go toward the star a little bit more quickly. They end up getting any pair of neighboring planets ends up getting a little squished a little closer together than they would otherwise. So if they migrate slowly, they end up here. But if they migrate really fast, they end up quite a bit closer. What does that mean? Basically, you're going to end up with these chains of orbital resonances of planets that are much more compact, much more closer together than the TRAPPIST-1 system. We think these form all the time, but they're held together by the gas disks. And so when the gas disk goes away, the TRAPPIST-1 system was stable. But we think most of the time, especially if these systems are a bit more compact, they're unstable. And so what do? Then they do actually the same thing that gas giants planets were doing, where their orbits start to cross and they have a dynamical instability. But these are small planets very close to their stars. They don't have enough gravity to start ejecting each other. Instead, they collide with each other. And so there's a phase of collisions, and you end up with systems that are more spread out, and they're not in resonances anymore. And they look just like the ones that we see. So we think this process of migration and then instability is pretty generic. And those 2 ingredients explain a lot of what we see in terms of both the solar system and exoplanet systems.
Now, when you look at the solar system, ours, and you say, well, there's strange aspects to that, do you think TRAPPIST-1 is also strange? In other words, do you think, when you look at it, do you say, that this is probably not a common situation?
That's a good question. When I had a paper predicting what we would see among super Earth systems before the Kepler satellite was launched, and I predicted that we'd see a lot of TRAPPIST-1s, and I wasn't the only one. A lot of people had thought this, that basically this kind of simple idea of planets migrating closer to the stars would predict that you'd often end up with systems that look just like TRAPPIST-1, where if you see one planet, that means that the whole orbital plane of all these planets is basically pointed right at you. And then you can see a lot of them. And they happen to be in this nice kind of configuration of resonances. But of course, that's not what we saw. It turns out that they're rare. There's some known. There's oh geez, I don't know the number off the top of my head, maybe five or so systems that have at least 4 or 5 planets in resonance. There are a few of them out there, but not a ton. So, I mean, TRAPPIST is still extra special in terms of some of its other characteristics, like being around such a puny star. It's perfect in some ways that it's around such a faint star, an object that's barely a star. It's almost a brown dwarf. It's only what, 9%, I think, of the mass of the sun, and what, 2,000 times fainter.
Tiny little dude. Yeah. Tiny, tiny.
Yeah. And so, that's really useful so that when the planets pass in front of the star, they block a lot of the light. Basically, the relative amount of information you can get anytime a planet passes near there is a lot higher than if the central star was brighter and washing out the signal. So it's super useful for looking at it in characterizing the planets later on, which is pretty cool.
Well, I got something more. So, building the ideal solar system, and people should look at your blog. There will be a link in the description below. And you've posted about this, that none of this is ultimately ideal, right? You could have a situation that's better.
Oh yeah, for sure. For sure. Yeah, this was a fun thing I did on my blog. It was one of the very first posts I did on my blog was to reimagine the solar system, where I was playing a game where I had to preserve all the planets in the solar system and all the orbits, but I could move around, planets to different places. And so I shuffled some things around, and I put Jupiter where Mars is, and I put Mars and I forget what else in orbit around Jupiter. And I played, some other games like that. And I ended up with arguably 7 possibly habitable planets in the solar system instead of just the one we have now. And so I was like, hey, that's pretty cool. And then it turns out that was the only blog post on my blog that anyone would look at or comment on. And so I decided to expand on this idea and then play this game I called trying to build the ultimate solar system of, if the goal was to design a system with the maximum number of potentially habitable planets, how would you go about putting that together? And so this is a weird combination of, how could such a system form and what ingredients could you put in place where if they were just put just so, they would still remain stable. And so given that I work on, planet formation and orbits and stuff like that, I kind of went through different parts of the process of, what kind of star do we want? What kind of planets do we want? And then the key thing that I played around with quite a bit is what are the orbits of these planets? And so the first time I did this kind of game, which was, I think it was like 10 years ago now, I ended up creating a couple systems that had 30, I think that each one had about 30 habitable planets. Some of them had some tricks to them. Basically, I crammed a bunch of orbits close together, but they were still stable. And then I also, in a separate system, I made a bunch of I basically put some gas giants, and I put planets as moons of the gas giants. And then I was also able to put some Trojans in there, which is a configuration where more than one planet is sharing the same orbit. And doing this, then I just put those 2 stars around each other and ended up with a system with like 60 planets in the habitable zone in one system. And then I kept going further and further. And I did series of tests where I created gigantic systems, mostly using co-orbital rings. This is something when I came across it, I didn't think it was real. But then I did a bunch of n-body simulations to really test this. And it turns out that it's totally stable. And it was kind of figured out about 30 years ago by people thinking about structures within Saturn's rings. And the idea is that a ring of planets is generally, you'd think that's not going to be stable, right? It shouldn't be stable, but it is under certain conditions. The planets have to have a minimum spacing between them. And you have to have at least, I think it's at least 9 planets within the ring, if I'm remembering right. And if that's the case, then a ring of evenly spaced planets will be stable in orbit. And so one thing that's pretty funny about this, and some people, this was Smith and Lissauer showed this, that for the Earth, for an Earth mass planet, at Earth's distance from the sun, the maximum number of planets that you could put into one of these co-orbital rings is 42. And so it's just like straight out of the Hitchhiker's Guide to the Galaxy, 42 being, the answer to life, the universe, and everything, which is awesome. And so I kind of built on this idea that they had and showed how you could have many rings in different configurations. and you could have up to, 400 or so Earth mass planets around a single sun-like star, all within the habitable zone. And then I even went nuts and I threw in some supermassive black holes and did a bunch of other fun experiments like that, just to kind of see what could be out there. And what I think is really interesting about this is these systems, I tested a lot of them with real simulation. So if they formed in reality, they would be stable. And then the question is, well, why don't they exist? If they could exist, then, should they exist? And you can imagine, well, could a ring of planets ever form? And the truth is, well, you can imagine it's not impossible if there was a really dense ring of dust like we see in those ALMA images of planet-forming disks that happen to clump in a very, very nicely, perfectly symmetric way. Could you end up forming a ring of planets like that? Maybe. Maybe you need to have a coin flips where you flip heads, 100 times in a row. And in that case, you can. I don't know. But if we ever do find a system that looks like that, it'll be amazing.
Well,
And in general, I think it's probably unlikely to form naturally. And so if
yeah,
you find one
but
like that, you kind of think in aliens, but I don't.
yeah, but that's my final question. Technosignature? I mean, could this be, if we ever saw this, seems to me, would be so weird that we'd be like, maybe aliens migrated that stuff in that way or did something. So is that, if we saw that, a really weird system like that, that almost looks constructed, at what point do we say, yeah, that might be that?
Yeah, that's a good point. We did a series of a few papers with David Kipping and a few other people where he came to me with this idea that if you wanted to construct a system like that, imagine there's some very advanced aliens out there that can move planets around. What if they wanted to create a system that would be recognizable as non-natural? And one idea that he had for such a system would be not a co-orbital ring or anything, although that's a candidate, of course. His idea was that you could have encode sequences of integers within these chains of orbital resonances. So we have systems like TRAPPIST-1 where each pair of planets is in a resonance, like 3 to 2 or 2 to 1 or 4 to 3. And what if you could put those in such a situation where they mapped out like, the prime numbers, consecutive prime numbers? So we thought about this, and it turns out that in our big database of simulations where we formed this kind of system naturally, we very rarely get that kind of structure. We get a lot of resonances that look like where the two numbers are apart by 1. That's called first order resonances. So that means like the 2 to 1 or the 4 to 3 or the 3 to 2. Those resonances are really common. But if you're doing consecutive primes, what do you have? You got 1, 2, 3, 5, 7, 11. And so some of those basically, 7, 11, that's a really weird one. We never get that coming out of simulations. And so what we did is actually Matt Clement was the one who actually did the simulations himself. He basically very gently nudged chains of resonances into a few kind of ideal resonant chains. One of them mapped out consecutive prime numbers. One of them mapped out the Fibonacci sequence, and we did a couple other ones like that. And he found that these systems, they rarely form. They pretty much never form in our simulations, right? Does that mean they never form in nature? Of course, we can't be sure. But if our simulations are an okay match to reality, they shouldn't really form naturally. But if they could somehow form, they would be stable. And we tested they would be stable for 20 billion years. They would stay stable even when the sun becomes a red giant and then collapses into a white dwarf, right? So these resonant chains, even though their orbits could actually expand during that case, they would stay stable. And so that would be a case like you're talking about where you could design a system and the system would look kind of non-natural on purpose to another civilization that's smart enough to figure that out. And there's other kind of ways you could do that. But things like those consecutive Fibonacci sequence numbers encoded, or just, rings of co-orbital planets, those were all kind of fit the bill of non-natural systems that you could, in theory, engineer if you had the capabilities.
Yeah, but you would be telling everyone in the galaxy that saw that we are really, really powerful, which is in a way scary. So thank God they would be distant. Thank anything that they would be very distant from us, because that would be a powerful civilization. Sean, thank you for joining us today. Everybody should check out Sean Raymond's blog and website. And Sean, give us the URL.
It's planetplanet.net.
Planet. Not hard to remember. All right, thank you, Sean. And I look forward to future conversations, hopefully.
Yeah, it was great talking to you. Thanks for having me.
All right.